Hello everyone. In the last video, we proved one theorem. Now we'll define subspace of a vector space now. So see the definition. I have already written it. So a non-empty set U of a vector space V over a field F is said to be a subspace of the vector space V if U is itself a vector space over the same field F with respect to the vector addition and scalar multiplication we defined on the vector space V. So when you call a non-empty set U as a subspace of a vector space V, firstly U must be a vector space, okay, with respect to the vector addition and scalar multiplication defined on V, and field must be the same, okay. So this is the definition of subspace. Next, the zero space, the singleton set 0, this always becomes a vector space, okay, and it is known as zero space or a null space, okay, you remember this. Next, the set of 0, that is the zero space, and the set V itself are trivial subspaces of, trivial means obvious, are trivial subspaces of a vector space V, okay. The zero space always is always a subspace of vector space V, and the set V itself is also a subspace of vector space V, okay, and these two are known as trivial subspaces, okay, and V is known as improper subspace of V, okay. Next we will prove one theorem which will give you the conditions for a non-empty set U to become a subspace of vector space V. So see the statement: a non-empty subset U of a vector space V over a field F is a subspace of V if and only if. So we have to prove two parts here, okay. So what I said, a non-empty set, a non-empty subset U of a vector space V over the field F is a subspace if U plus V belongs to U for all UV belongs to U, and alpha into U belongs to U for all alpha belongs to F and for all U belongs to U. This is your vector addition and this is your scalar multiplication. If these two operations are defined on non-empty subset U of V, then U will become a subspace of vector space V, okay. So we have to prove this, and we will have two parts here. In the first part we will prove these two conditions while assuming the set U as a subspace of V, and in the second part we will assume these two conditions and we will prove the set U as a subspace of V, okay. So let's start. Let V be a vector space over a field F and U be any non-empty subset non-empty subset of V, okay. Now number one, let U be the subspace of vector space V. Okay, and we have to prove number one, the vector addition u plus v belongs to u for all uv belongs to u, and scalar multiplication alpha into u belongs to u for all alpha belongs to field f and for all u belongs to u. Okay, so as u is the subspace of vector space v, then by definition of subspace u itself becomes a vector space, as u is subspace of vector space V. U is a vector space by definition of subspace. Okay, now let uv be any two elements of u and alpha be any scalar from f. Then we have u plus v belongs to u by closure property in u, and alpha into u belongs to u. It is scalar multiplication defined on u. Okay, we have u plus v belongs to u for all uv belongs to u, and alpha u belongs to u for all alpha belongs to field f and for all u belongs to u. Okay, so this is our first part. Now we assume these 2 points and we will prove u as a subspace of vector space V. Okay, number 2. Here we will assume, let us assume number 1, that u plus v belongs to u for all uv belongs to u, and number 2, alpha u belongs to u for all alpha belongs to field f and for all u belongs to u. Okay, and we prove u is subspace of vector space V over F. Okay, so when you say u is a subspace of vector space V, if u is a non-empty subset of V and u becomes a vector space over a field F with respect to the vector addition and scalar multiplication defined on V. So we have already written in the given part of this proof, u is a non-empty subset of V. Okay, so we now prove u is a vector space. Okay, since u is non-empty subset of vector space V over field F. It is given, we prove U is vector space over the field F. That is, we have to verify, that is, we verify V1, V2 and V3. So we will go one by one. So V1 U plus is abelian group. In order to show U plus is abelian group, we just show that U is a subgroup of abelian group V, that is, for all UV belongs to U, U minus V belongs to U. Okay, so let UV belongs to U and alpha belongs to the field F. Then by 2, by 2 means our given part, this we have U and alpha V belongs to U. Okay, which implies U plus alpha V belongs to U. Here we have used number 1 by 1, this one. So now U plus alpha V is a member of U, and as alpha is a member of F and F is a field, we put alpha equals to -1. And what will we get? U plus -1 V, which is same as U minus V belongs to U. Okay, by theorem you can write, because this we have proved in the last theorem. Okay, so in this way we got U minus V belongs to U. Therefore U is a subgroup of abelian group V. Okay, this implies U is abelian group. Okay, so V1 is verified now. Now we verify V2, that is, scalar multiplication must be defined on U. We have alpha into U belongs to U for all alpha belongs to F and for all U belongs to U. By number 2, this part. Okay, we have this alpha into U belongs to U for all alpha belongs to F and for all U belongs to U. This is what the scalar multiplication. Okay, so therefore scalar multiplication is defined on U. So V2 is verified. Now we verify V3. Since V is vector space, then we have then we have for all alpha beta belongs to field F, and for all u v belongs to V, alpha into u plus V is equals to alpha into u plus alpha into V. Alpha plus beta into u is equals to alpha into u plus beta into u. Alpha into beta into u is equals to alpha into beta into u, and 1 into u is equals to u. All true in V, as U is non-empty subset of V. We get alpha into U plus V is equals to alpha U plus alpha V. Alpha plus beta into U equals to alpha U plus beta U. Alpha into beta into U equals to alpha into beta into U, and 1 into U is equals to U. For all U V belongs to U, and for all alpha beta belongs to field F. Okay, therefore V1, V2, V3 are verified. Therefore U is a vector space over field F. Okay, and U is a non-empty subset of V. This implies U is a subspace of vector space V over field F. Okay, so hope this proof is clear to you. So you just remember that a non-empty set U will be a subspace of a vector space V if these two conditions are verified. Okay, so this is all for this video. The corollary to this theorem we will prove in the next video. Okay, thank you.